Yeah, please be seated. Okay, welcome back to the second morning session. And the first talk is given by Hong Liu, and he will report on emergence of space and time in holography.
Okay. I want to thank the organizers for bringing us to this wonderful city, this wonderful university, and this wonderful venue. And I also want to thank them for the opportunity to present the research here. So, So this is some work we did recently with Neuthauser in these two papers, and then to appear. Okay. Good. So, outstanding question in holography is, starting from early days, is how box space-time and associated geometric structures arise in the boundary description. Okay, so that also includes, of course, the causal structure, and there have been many hints, and also there have been much said about this question. So today I would like to give some new perspective on this question. So first I would like to emphasize that geometric notions such as local space-time regions, surfaces, horizons are sharply defined only in the G Newton goes to zero limit. So by G Newton goes to zero, I mean perturbative series in G Newton to any finite order. Okay. And this translates into the boundary series into the n equal to infinity limit. So if we want to try to answer this question, so that should be the stage we formulated this question. Okay. So the question I would like to phrase is that can we pinpoint some precise mathematical structure, say in the large n limit, that is responsible for this emergence of various geometric notions? Okay. And my slogan of today is that the box space-time is a geometrization of emergent boundary type 3 1 algebras. And this statement can be separated into two parts. First, I will emphasize actually in the boundary series in the large n limit, there's ubiquitous emergence of type 3-1 volume algebras. And I will argue they can be one-to-one mapped to box space-time regions. And also, then the properties of such emergent type 3-1 algebras then leads to geometric notions, such as horizons, times, causal structures, etc. Okay. So I would like to talk about three examples. So one is the emergence of horizon and Kruskal-like times in ADS internal black hole and the associated causal structure. And the second is that this emergent error-correcting properties, say for holography, and also talk about a picture of RT surface without entropy. And then the third, I will talk about more general formulation of such region duality, which does not use RT surface. Okay. Yeah, so this is like entanglement wedge without RT surface. So first, let me make some remarks on the large n limit. So say as a prototype example, let's consider n equal to 4 super Yang-Mills series with gauge group SUN. Also, this should be a script n, somehow didn't show up. Okay, so in the large n limit, one important feature is that many states and operators which are well-defined at finite n, they actually don't have a well-defined large n limit. That means that in the large n limit, they drop out of your spectrum. Okay, and as a consequence of this dropping out from your spectrum, the structures of your Hilbert space and operator algebras actually undergo dramatic changes in the large n limit. So here, for example, the full Hilbert space actually splits into disconnected GNS Hilbert spaces around semi-classical states. By semi-classical states, I mean those states which have a classical gravity description. Okay, such as say vacuum or thermophile double state, etc. Okay, so these are the states which have a well-defined large n limit, and then we can build the GNS Hilbert space around it. And then secondly, that in a large n limit, the operators which survives are generated by single choice operators. Okay, so essentially the operator algebras are those generated by single choice operators. And such operator algebras have the following features. So the first is that the single choice operator algebras at different times actually are independent. Okay, and also the structure of such an operator algebra actually can become state dependent. And the third is this, as I mentioned, the ubiquitous emergence of type 3 one volume algebras. Okay, so now let me just first say a few remarks on this feature. So consider, let's consider general quantum field theory. Say if you consider some operator time t, and then this operator at time t then can be expressed in terms of operator at t equal to 0 from standard Heisenberg evolution. So if you look at the Coastal diamond and look at two Cauchy slices and look at the operator algebras associated with these two Cauchy slices, A1 and A2, and then because of this feature, and then this A1 just equal to A2, because anything on A2 can be expressed in terms of A1. But this is not the case for single choice operators. So if you, in a large n limit, if you look at single choice operators, the single choice operator at OT cannot be expressed in terms of single choice operator at t equal to 0. So if you do Heisenberg evolution, inevitably that will evolve operators go beyond the single choice operator at t equal to 0. So that means that now if I look at for single choice operator defined on these two different Cauchy slices, actually they're not equivalent. Okay, so this is a very simple but actually important element which will have many implications. Okay, so the first example I'm going to talk about is internal black holes in ADS, which has been argued many years ago, say to be due to the two copies of your CFT in the sum of your double states. So we all know that in this black hole geometry, the boundary time stops at the event horizon, okay, only covers the right region and the left region. So it has been a mystery, say how do we describe this future and the past region, say in terms of the boundary theory, okay? And how do we describe the Kruskal-like time? Because this boundary time can only, corresponding to the Schwarzschild time. And also, what is the boundary, say, signatures of horizons and associated causal structures? Okay. So, so here I'm just repeating, say the black hole is described by two copies of CFT, which I call CFT-R and CFT-L in the sum of your double states, say for the temperature greater than the Hawking-Page transition. Okay. And at finite n, the bounded operator algebra, say let's take CFT-R or CFT-L, is a type 1 volume algebra because there's a well-defined Hilbert space, etc. But as I mentioned, this type 1 volume algebra is actually not relevant for large n. Because in the large n limit, many operators in this algebra actually they're not well defined. Okay, so in the large n limit, we should concentrate on algebra generated by single choice operators. Say I call them AR. And then the action of this AR, say all these single choice operators on the sum of your double state, then actually generate a Hilbert space. So we can call it, so this is like Hilbert space of small excitations, say around the sum of your double state. And then the nature of this algebra, then is actually determined by representation of this algebra in this Hilbert space. Okay, so in this way, and this single choice operator algebra actually becomes state dependent. Okay, so to emphasize that it's the representation of the AR in this Hilbert space matters, so I give a different name and call it MR. Okay. So the claim, which I will not have time to explain, the claim is that for if you below the Hawking-Page transition, then this single choice operator algebra is actually still a type 1 volume algebra. But when become greater than the Hawking-Page transition, this becomes type 3 one volume algebra. Okay. And so this will have important implications. So first, let me just mention that say if we look at the operator algebra, so this is the single choice operator algebra in the CFT in the right region and in the left region, and then from the duality, then we should identify them with the operator algebra in the bulk in the right region and the left region of the black hole. And so this MR tilde and ML tilde can be defined, say, on a single Cauchy slice, say, of a black hole geometry. Okay, for example, the T equal to 0 slice. Actually, more precisely, when I identify these two algebras, I actually don't really know the F and the P region. I don't even also know whether this M tilde R algebra and M tilde L algebra, they're connected or not. Okay, so the physics outside the horizon during this identification essentially just tell us MR is identified with MR tilde and ML is identified with ML tilde, and what happens, say, in between, and then should come out from the properties of this theory. Okay. So now let's think about how do we do the time evolution. Yeah, so in order to see this future and the past region, then we need to ask about the time evolution. So now let's think about time evolution, say on the gravity side. And so this is the geometry. So we have this T equal to 0 slice, which we have this operator algebra in the bulk, which identified with those in the boundary theory. Okay. And so due to this identification, and then suppose you evolve this Cauchy slice to some other Cauchy slice, and because of the bulk, you have just ordinary Heisenberg evolution, and then that's this time evolution just corresponding to some automorphism of this algebra. Okay, so from the boundary point of view, say this bulk time evolution should be just mapped to the boundary automorphism of these two boundary algebra, MR and ML. So we can do it conversely. If we understand the boundary automorphism of this MR and ML, then we should be able to understand the bulk evolutions. Okay. And so there's a standard time which are generated by this right Hamiltonian minus the left Hamiltonian. And so that's the below, this is the standard Schwarzschild time, okay, which generate the time slice like this. So if you evolve by this kind of Hamiltonian. And so I want to emphasize 2 points about this. So one thing is that this can be used to generate the bulk time regardless of the type of the algebra of MR and ML. So whether this is type 1 or type 3, type 2 doesn't matter. This always exists. And the second point I want to emphasize is that evolution by HR and the plus HL is actually not well defined in the Lagrangian limit. So from the bulk point of view, evolution by HR and plus HL actually does not have a consistent bulk description. Okay. So now if we want to describe some kind of Kruskal-like evolution, then we have to look for something else. Okay. And now it turns out if MR and ML are type 3-1, and then there's a very special property for type 3-1, which is not for other type of algebras. So this is something called half-sided modular times, which I don't have time to explain. So the claim is that if they are the type 3-1 algebras, then there are new emergent times, which are specific only for type 3 algebras. Okay. And now it turns out they can be the evolution under such kind of half-sided modular times can be mapped into this kind of Kruskal-like evolutions, which can take this slice, go to in the future, which cross the horizon, take you into the future region, or take you in the past region. Okay. And in particular, under this half-sided modular times, and you can generate the future and the past region, and then you also see the sharp boundary signatures of the horizon. Okay. Okay, just to summarize, so we start with this picture, say identification of the algebra of the MR with the M tilde R, ML, and the M tilde L, and then we say for T greater than Hawking-Page transition, the algebra is type 3-1, and then we can generate this full space-time structure, say, of Schwarzschild, internal Schwarzschild black hole. On the other hand, if your T is smaller than Hawking-Page transition, as I mentioned, this MR and ML, they actually remain to be type 1. Then in this case, there's only one time available. It's your HR minus HL. And in this case, you actually see the two disconnected space-time. Okay. So the fact here, you see a connected space-time. Here, you see a disconnected space-time just determined by the algebraic structure in the Lagrangian limit. So if I want to make it into a slogan, so I would say this causal connectedness, as you see in the Schwarzschild black hole, is actually from emergent type 3-1. So actually, I want to advocate this types is something more precise than ER equal to EPR. So previously we say that this washout black hole or more general geometry, they're connected is because the left and the right are entangled. Okay, and here is a more precise notion because this algebraic structure gives you more information, etc. Yeah. Okay. So now let me go to the another question to the entanglement wedge without entropy. So now let's consider the boundary CFT in the vacuum state, and now let's consider some boundary region R. Okay, and so in any quantum field theory, if you consider operator algebra in some region R, and then it's always a type 3-1 algebra. Okay, and so at finite n you get the type 3-1 algebra. Then as I emphasized, actually this is not relevant in large n limit, and again, many operators in this type 1 algebra, they just drop out in the n go to infinity limit. And in the n go to infinity limit, again, you should concentrate on the single trace operators. Okay, so this AR in the causal completion, so we consider the single trace operators are defined in the causal completion of R. Again, you can argue this is an emergent type 3-1 algebra. And again, this is the states dependent. So here we are considering the vacuum state. You can also consider some other states, say which have the Bach, map to some Bach geometry, and then you can consider some region, and then this AR representation in that Hilbert space generated around that state. Then again, define some kind of emergent type 3-1. Okay. So now we can reformulate this so-called entanglement wedge reconstruction into the following. So I will now define the entanglement wedge in the algebraic way as the Bach space-time region whose operator algebra, operator algebra is identified with this emergent type 3-1 algebra. Okay. So this in principle provide a precise definition, say, of your this entanglement wedge, in the n go to infinity limit. And so this provides a way to derive Utagalagi surface, say, without using minimal surface, okay, without using entropy. So now let me just give you some examples, so you can work this out in some examples. Say, for example, let's just consider, say, a two-dimensional theory, the two-dimensional CFT. The boundary, so this is, say, in the Poincare patch. So this is the radial direction, and so this is the boundary. So if we consider the half space, okay, the half space, that's my region R. And then if you look at the single trace operator algebra in this region R, and you try to identify the region in the Bach, the region, the algebra of the region in the Bach, which identified with this, the single trace operator algebra in this region, and then you find it's given by the causal completion of this region, say, you just extend it along the z direction. Okay, and of course this is precisely this boundary is precisely just the RT surface for this half space. Okay, you can also do this. Say if you take R to be a segment, and then you find that the Bach region just a half circle, and then again this the boundary give you the RT surface, say for a segment. So now you can consider a slightly more complicated example. Oh, yeah, somehow the color didn't show. Okay, yeah. Anyway, so now if you consider a region given by this, the joint of these two half line, so this half and plus this half, okay, and then you can ask what is the region of the Bach algebra. Say dual to the boundary series algebra in this region. It turns out, so this region outside the circle is supposed to be shaded, and you find is all the region outside the circle. Okay, and so this is a non-trivial example because this is an example which the entanglement wedge is actually greater than the causal wedge. The causal wedge for each region is just just a two copy of this. Okay, you just have again, I will have another diagram which shows the causal wedge. So the causal wedge, you just have two copies of this, but the entanglement wedge is bigger, including also the region of the circle, the region outside the circle. Okay. Good. So, So you can also consider even more general algebras in the boundary theory. So the general statement is I would like to advocate. So emergent type 3-1 algebra actually always dual to Bach operator algebra in some space-time regions. So now let's consider some more unconventional examples. So let's consider CFT. Say again, let's go back to the thermal field double example. Let's consider this CFT R in the thermal field double state. And now so this is the boundary space-time. Let's consider, say, 1 + 1 dimension. So this is the spatial direction, this is the time direction. So now let's consider the algebra of operators formed by all the single trace operator for t smaller than 0. Okay, so this is not the standard operator algebra we consider, which you only consider some region. Okay. The reason that this is a non-trivial algebra is because of precisely the property I mentioned earlier, that single trace operator algebra for different times, they're inequivalent to each other. Okay, so you can argue actually all this operator algebra for t smaller than 0, they form a non-trivial type 3-1 algebra. And then you can argue, so we argue that this is actually dual. This is important. Somehow didn't show up. So this is dual to some region in the Bach. Okay, so this is you can just draw. Maybe I can just draw it. You say there's a pen, I can draw it. Oh, all right. So just dual to this region. Oh, does not work in PowerPoint? Oh, okay. Okay, that's fine. Anyway, it just dual to some region in the Bach. Okay, just imagine there's some region in the Bach which is dual to this algebra. Okay, and somehow this unconventional type 3 von Neumann algebra is realized in the Bach through some geometric region. Okay, so that's the point I want to convey. And similarly, you can consider, say, CFT2 in the vacuum. Okay, CFT2 in the vacuum, and consider consider time band like this. Again, this is the spatial direction, and this is the time direction. We can also put the x direction on the circles. Okay, and so let's consider the algebra in this time band between T1 and T2, and then you can argue that the operator algebra in this space-time region is actually dual. So the Bach dual for this CFT2 is the cylinder. Okay, I didn't draw the circle direction. So this is the radial, this is the time direction, this is radial direction, and then there's a circle direction. Okay, and so you should imagine there's a rotation, there's a circle direction. So the claim is that this time band, the algebra in this time band is dual to the region in this kind of causal wedge, a radial causal wedge outside some radius. Okay, so if you look at it from the top, it behaves like this. Okay, it behaves like this. Okay, good. So this is the region, the operator algebra in this region, which is dual to this time band. Okay. Okay, good. So let me just again go back to this point. So we want to argue an emergent type 3-1 von Neumann algebra. They have some one-to-one mapping to the Bach operator algebra in some space-time regions. Okay. And the operator algebra in some space-time regions can be considered as an algebraic way to describe, say, geometrically just some space-time, the Bach space-time regions. So and then this way we can argue. Is this 2 or 1?
You have 5 minutes.
Oh, right. Okay, good. So now we have So now you can argue this emergent type 3-1 algebra then should be one-to-one correspondence with some Bach space-time regions. And then the slogan again is that the box space-time is a geometrization of emergent type 3-1 algebras. Okay. Okay, so maybe I will very quickly go through these slides. So one important property of the holographic when you do this sub-region duality is that certain operator in some Bach region, you can have multiple descriptions. So you have, say, the Bach description is highly redundant, and then it has been given some beautiful interpretation in terms of quantum error corrections, and this provides the guiding principle for building many toy models of holography using finite dimensional Hilbert spaces or type 1 algebras. But however, the story is not completely satisfactory because the physical origin of these quantum error correcting properties remains unclear. And as I mentioned, since this is a property pertaining to classical geometry, and in real holographic system, this should be intrinsic properties of the Lagrangian limit. Okay. Okay. Oh, right. Sorry. So yeah, indeed. We should be able to. Okay. Yeah. So let me just show the future, some future perspective. Okay. Thank you.
Yeah, thank you very much for your talk. Are there questions?
Is there any signature of the black hole singularity in the algebraic picture?
Yeah, I think that's a very good question. We tried to look for it. We haven't identified it. I believe there should be, but we haven't identified it. Yeah.
I see. Thank you.
So how much of what you said applies to, say, finite to Foot coupling large n equals 4 super Mills?
Sorry, say it again. I didn't quite.
How much of what you said apply to finite to Foot coupling but large n?
Oh, yeah. Yeah, that's also a good question. So in principle, what I said so far does not strongly depend on the coupling. So as far as it's not free theory, you may expect, I would expect this type 3-1 algebra should still emerges, and but I think this is a question should be investigated very seriously. Yeah. Mm-hmm.
Other questions?
Is there a manifestation in Euclidean signature of these discontinuities that you discussed? Is there some simple Euclidean picture or observable?
Sorry, Euclidean signature of what?
In Euclidean signature, is there some calculation you can do to observe some of the discontinuities you discussed in the operator algebra?
Continuity? Sorry, there's one word I didn't quite hear clearly.
If you go to Euclidean signature, is there a manifestation of a Euclidean calculation of the discontinuities of your operator algebras in Lorentzian?
You should be able to see it in Euclidean. It's just a little bit more indirect. So to see this emergent type 3-1 related to the spectrum of the modular Hamiltonian, say the spectrum of the modular operator, and say if you calculate the correlation functions in Euclidean, in principle, you may be able to deduce spectrum of the, say, modular operator indirectly from there. But I don't know a direct sharp signature.
Quick clarification question. In your slide on entanglement wedge reconstruction, were you dividing the boundary into 3 regions? Is that right?
Sorry, you say for which one?
The entanglement wedge reconstruction part.
Okay.
I'm trying to understand the calculation.
Yeah, this one.
There. It looks like you're dividing the boundary into 3 regions.
Yeah.
But there's no transition for 3 regions. You need 4 regions.
So here you do have 4 regions. So if you translate this into the cylinder, this corresponding there's a point. separate, because the Poincare patch is the cylinder which you remove a point. And so essentially here you do have 4 regions, just one region is a point.
Okay, my question was about that point. Okay, thanks.
Yeah.
Okay, let's postpone all further questions to the lunch break. So next speaker is Nick. First, let's thank the speaker again.